All right, so in the last video, we were looking at properties of waves. We looked at reflection as an important property of a wave, which is the bouncing of light. So in this video, we start with the property of waves that we call refraction. So refraction. So the question is, what is this refraction? So refraction is the bending of a wave. So normally refraction will occur when a wave travels from one medium to another. So what do we mean? So a wave can travel from air medium to water medium, or can travel from vacuum, which is not a medium at all. So it can travel from vacuum to air. And at the interface between vacuum and air, the wave is going to bend. So that bending is called refraction. You can see here there is an interface between deep water and shallow water, and you can see that the wave has bent here. So we have bent or bent the wave. Now, in terms of diagram, we are also going to draw a ray diagram. So you can see that we have an incident ray. So the ray that strikes this interface. So we have an interface between air and water. And we have an incident ray. This is in air medium. It hits the interface between air and water. So air and water interface. Once it hits here, we see it is bending. So it is coming like this, and it bends at the interface. That bending is called refraction. Now, if you are drawing diagrams, you are going to have an incident ray, which is this ray. Then you are going to have a refracted ray, which is the ray after bending. Look at the direction of the arrow. The incident arrow has a direction of the arrow going forward to a surface. The refracted arrow also has the direction going forward, but that is from the surface. So this is to the surface. This is from the surface. So we need to take note of that. And also we have angles. We have angle of incidence, which is here. And then we have angle of refraction, which is here. So if you are dealing with diagrams like this, you need to know what is the angle, or how do I identify the angle of incidence? How do I identify the angle of refraction? What is my incident ray? What is my refracted ray? What is my normal? What are my two mediums? Now, sometimes you have actually three mediums or three media. Here we have an incident that is coming from vacuum, and it hits the interface between vacuum and glass. Then it bends and then hits another interface between glass and water. So each medium has what we call a refractive index, starting with vacuum. So I'm not going to talk much about refractive index, but I'll just tell you that vacuum, by convention or by agreement, vacuum has a refractive index of 1. So the mediums, like the more dense the medium or the thicker the medium, the higher the refractive index. So we see that water has a refractive index of 1.3, and glass, which is more viscous or which is thicker than water, has a refractive index of 1.5. If we have something that is even thicker than glass, that one is going to have a refractive index of greater than 1.5. Now, if we talk about bending of light, if we move from also these two are normal, what we call normal lines. So I'll call them normal lines. They are always perpendicular to the surface of what we are dealing with. I mean, this is perpendicular to this surface at 90 degrees angle. So those two are normal lines. Now, important statements. If moving, so moving from low refractive index to higher refractive index, what happens? I just need to let me get rid of something. Let me discard and then I'll just write again. So so moving from low refractive index to higher refractive index. So if you move from low refractive index, like here, air is low refractive index, glass is higher refractive index. Now, if you do that, the ray bends towards the normal. So ray bends towards the normal. So if your normal is this one, and you are moving from low refractive index to higher refractive index, the ray will bend this way. So this is bending towards the normal. So moving from lower refractive to higher refractive index, the ray bends towards the normal. So you can see that here, air has a vacuum has low refractive index and glass has higher refractive index, and the ray is bending towards the normal. Now, moving from higher refractive index, higher refractive index to low refractive index. Now, in that case, the ray bends away from the normal. So you can see here, glass has a refractive index of 1.5 and water has a refractive index of 1.3. You can see that the ray is bending away from the normal. So you can see that the ray is bending this way, or is bending this way away from the normal, while here it is bending towards the normal. So the difference between the refractive indexes or indices of the two mediums you are dealing with will determine how the ray is going to bend. Is it going to bend towards the normal line, or is it going to bend away from the normal line? So let's take note of that. And another important thing is, when a wave moves from one medium to another, there is something that changes. So when a wave moves from one medium to another, when a wave moves from one medium to another, one, frequency remains the same. So frequency of the wave does not change. But there is something that changes. Wave length, wavelength changes. Also, velocity of the wave changes. So we need to take note of that. If the wave, like light in vacuum, has the velocity of 3.0 times 10 to the power 8 meters per second, light in glass has velocity less than this value. The same thing, light in water has a velocity less than that value. So if you change mediums, the velocity of the wave changes, and the wavelength of the wave also changes. But frequency does not change. Frequency remains the same. We have a third property of waves that we call diffraction. Now, if you have something like a slit here, and you have a wave coming here as lines, when the wave hits this slit, it begins making ripples. This type of situation is known as diffraction of a wave. So diffraction is just the spreading of waves around a slit or an obstacle. That's what diffraction is about. So that's a property of a wave. Then there is another property of a wave that we call interference. Interference occurs when waves from two sources or three sources, when they meet at a certain point to produce a wave. Usually when two waves meet, they are going to produce a wave of different magnitude or different amplitudes, and we'll see what that means. So I suppose you throw two rocks in water. Each rock is going to make its own waves. Each rock is going to make its own ripples. And these ripples are going to cut each other. So you can see that, let's say this rock here has these ripples. You can see the ripples, you can see the crest, and you can see the troughs down there. And this one also has its own ripples. You can see the crest there, you can see the troughs down there. So these ripples, they are cutting each other. You can see here where they are cutting each other, the wave is getting bigger. I mean, where the crests are cutting each other, the wave is getting bigger. But you can see where the troughs. So this is a trough, is cutting a crest. It's like there is no wave there. The waves are canceling each other. So when you talk about interference, you have two waves from two different sources. The waves are going to cut each other. They can cut each other as crests, or they can cut each other as troughs. Or a crest can cut a trough. So when we talk about waves, we have what we call two types of interference: destructive interference and constructive interference. This type of interference, destructive interference, a crest cuts a trough. That is destructive interference. So you can see that here we have a crest here and we have a trough here. When they cut each other, what happens is they cancel each other and it becomes flat, like the wave is gone. That is destructive interference because they destroy each other. Now we have constructive interference. In this type of interference, crests will cut crests and troughs will cut troughs. And because of that, they enhance each other. For example, if we have a small wave here, if we add another wave to this wave, what the result is, you're going to make a bigger wave because that wave is double. the two waves that are cutting each other. This is what we are saying. So if you add two waves, you make a bigger wave. And if the waves are in sync with each other, they are going to give you a bigger wave. So normally constructive interference will occur when waves from two coherent sources meet to produce a wave of greater amplitude. So you can see the amplitude from here to here is greater than the amplitude from here to here. So we have kind of doubled the amplitude. While constructive interference occurs when the crests of one wave are over the crest of the other wave, so they cancel each other. This is what is happening. You can see crest versus trough, trough versus crest. They cancel each other to make just no wave at all. So this is what we are saying. Like if you drop a rock here and you drop a rock here, these rocks are going to make ripples. So these dotted lines are the troughs. The solid lines are the crests. So you can see where the dotted line meets the solid line, like here, you have destructive interference. Everywhere the dotted line means the solid line, it means the trough is cutting the crest. You have destructive interference. Now, where two solid lines meet, you have constructive interference. Where two dotted lines meet, you have constructive interference. Because this one is a crest, this one is a crest. So two crests meet, they make a constructive interference. This one is a trough, this one is a trough. Where the two meet, they enhance each other. They make a constructive interference. So they will make a wave that is deeper than before, or they will make a wave that is higher than before. That is constructive interference. So also we really talked about frequency of a wave as the number of cycles per minute, but we also talked about time period of a wave. So actually there is a relationship, a formula relationship between frequency of a wave and time period of a wave. So time period of a wave is given as 1 over frequency, 1 divided by frequency, which means frequency of a wave is also given by 1 divided by time period of a wave. So that's a formula that you can use. So this is just showing that relationship between frequency of a wave and time period or periodic time of a wave. So we have another wave that we call standing waves. Really, standing waves have what we call nodes, or we can say they are just stationary waves. So suppose you have two waves, like you have a wave moving this direction and you have another wave moving this direction. So they have the same wavelength. So these waves, they really look like they cancel the movement. It's like they are not moving, they are just standing. That's why we call them standing waves. So they are stationary waves because there are two waves that are going opposite direction, but they have the same wavelength, the same frequency, the same amplitude. And because they are canceling the direction, they look like they are not moving. That's why we call them standing waves. So like if you take a rope, I think we have what we call a battle rope, where you vibrate the rope up and down. Initially, you are going to have a forward wave, but when it hits this surface, the wave will start coming back here. So eventually, you just have a wave like it's not moving in any direction at all. It's just moving up and down. It's just vibrating without changing direction. So a standing wave has what we call nodes. So nodes are areas of no movement. No movement. At nodes, there is no movement. And then we have antinodes. Antinodes are areas where you can see vibration. So each standing wave has a node, has an antinode. At a node, there is no movement. At an antinode, there is vibrational movement. But we don't have directional movement at all. We don't have this directional movement for a standing wave. The distance between two nodes or two consecutive nodes is wavelength, which is lambda, times half. So the distance is half wavelength. Remember, wavelength is one cycle, which means we are moving from here all the way to here. And a node is just the distance from here to here. So that is half the wavelength. The distance between an antinode and the next node is quarter of wavelength. So we are talking about the distance between here to here is a quarter of wavelength. Lastly, we are going to talk about an important effect called a Doppler effect. Now, an example is if you are like standing somewhere and an airplane is coming from a far distance. So you have a person here, and then you have an airplane coming from this way. There, with its wings. As the airplane is approaching, as it is approaching, the sound becomes loud. So as the airplane is approaching you, the sound becomes loud. But as an airplane is moving away from you, the sound becomes quieter. It becomes less loud. So that effect is explained by what we call the Doppler effect. So Doppler effect is just the apparent change in frequency of a wave due to the motion of the source of the or the observer. So this is the source of sound. As it is moving closer to you, the frequency changes. As it is moving away from you, the frequency also changes. Now, the observed frequency is higher when the source and the observer are getting close. Like as this airplane is getting close to this person, the frequency of sound will increase, and therefore the person will hear the sound clearly or loudly. The observed frequency is lower when the source and observer are getting further away. So as this plane is moving away from the person, the frequency of the sound becomes less and less, or lower and lower, and then the sound becomes quieter. It becomes less loud. That's what we call Doppler effect. So what does it mean? Think about approaching water. So there is a person here, and there is water approaching that person. You know, the front of the water, the waves are close together in the front of the water, but the back of the water, the waves are further apart from each other because their strength has decreased. While in front of the water, the waves are very close to each other. So as the waves are approaching the person, they are approaching the person using the front of the water, or using the front here. So you can see the frequency of these waves is higher than the frequency of these waves. That's what happens with sound. As an airplane or a vehicle is approaching a person, the waves are like the front, are in front of the vehicle, and the waves get closer together, which increases their frequency. But as the vehicle is leaving the person, the trailing waves, the waves at the back of the vehicle, are getting longer and longer, and therefore their frequency is decreasing. And as such, the sound becomes lower and lower. So that is what we call the Doppler effect. So this is what we mean. If something is going in front, you can see the waves are close together, higher frequency. If something is leaving, you can see the waves are trailing here. They are really further apart from each other, and therefore lower frequency, and the sound decreases. While here you have high sound, and here you have low sound. The reason is the frequency changes. Something approaching has high frequency of waves, and therefore high sound. Something leaving has low frequency of waves, and therefore low sound. So some examples, I just looked at the example of a plane. You can talk about a racing car. So it's like, ooh, ooh. So as it approaches you, you can hear the sound, like strong sound. As it leaves you, yeah, no sound at all. So that is an example of a Doppler effect. Not an application, but just as an example. But police apply it in speed traps. So they know an approaching vehicle, they can hear it from a distance because it is approaching, and the frequency of the waves is high. They can hear it from a distance. Also, astronomers, they use Doppler effect to measure the redshift of galaxies, but that will not be our uh, focus. So really, uh, that is it about waves and motion. Thank you.